Okay, you guys can hear me okay, I assume. So we're going back a little bit to modeling. I want to talk about some ongoing work, and I have to maybe give a slight, not apology, but just say that this is really fresh work, it's really ongoing work, and I figured I wanted to talk about the stuff that I'm currently excited about instead of showing some old results. So some of this will kind of be a teaser presentation of things to come in the future, and some initial quite interesting results. I should also say that this is work done in collaboration with Evan O'Connor at Stockholm University, and then Sean Couch and Carl Fields have done a lot of the code development for one of these projects. They developed a specific branch of Flash. I'll get back to that later. And then this relies on 2 computational grants on Lumi, which is this supercomputer in Finland. I should mention all of this bookkeeping. There will be 2 parts. The first part will be kind of stellar evolution, and then I will move on to the second part. I will show some initial results from some kind of eventually what will be late time simulations and focusing on the gravitational wave emission. So, I mean, these are the kind of introductory slides that I always show when I go to these conferences, and you would think this is a conference about supernovae and gravitational waves from supernovae, so I wouldn't have to show these slides. And then we also had a great talk yesterday from Bernard explaining all of this. But I mean, that's already 1 day ago, so maybe I should recap stuff a little bit. And there's a point to having this here. So I mean, we all know this picture, right? This kind of standard scenario that by now has been fairly well established. And we could have all of these more exotic scenarios. We could have very rapidly rotating progenitors and stuff like that. But for most of the scenarios, or for most of the core collapse, we expect the neutrino-driven mechanism to be the thing that is going on. So, you know, you have your massive star, and it runs out of hydrogen, starts to burn helium and heavier elements. You get the iron core, and the iron core collapses, and the collapses eventually halts. You form a proton-neutron star, and the neutrino streaming away from this thing eventually heats this stalled shock front, and then you blow up the whole star. And the turbulence in this layer is very important, and it's very interesting because, of course, that generates gravitational waves. And this is kind of where we stand right now, and this is the basic scenario that we have, well established, right? And I would kind of like to just second the thing that has been said here many times, that this scenario, you know, this is kind of, there is a lot of spread and a lot of uncertainty in the input physics, but this is pretty well established now, and we have some convergence between different groups, which I think is an important point for us modelers to convey to people who do signal analysis, right, and to look at the gravitational waves. So when we have established a basic scenario, the next questions that you want to ask start to become very detailed questions. And one question that I see quite often pop up is, so which stars explode, right? Like, can we start to say something about the distribution of stellar mass black holes? And of course, this is a very interesting question, and a question we should take very seriously. But if you want to start talking about which one of these individual stars are exploding, well, you see them there, then you really need to know your progenitors. And to this day, most core collapse simulations, they start from spherically symmetric simulations, right? This picture in the middle is clearly wrong. And this has been well established, right? There's many papers, I list a few examples here, that have shown that if you take the asymmetries of the progenitor into account, it can not only alter the dynamics slightly, it can alter the outcome. You get a black hole or you get a neutron star, right? So obviously, we need to move away from this spherically symmetric picture. But of course, that comes with its own set of challenges. And so I find myself doing something that I never thought I would do, which is stellar evolution, which is a very difficult field. So what I want to do is that I want to start developing models and publishing models that have all of these asymmetries in them, and then try to, well, first of all for myself, because I want to start from these models, but I also want to try to see if people are interested in using these models, and we can move to starting our simulations from more realistic initial conditions, with some caveats, of course. So the first part, what we do is that we take MESA models, we evolve them until the onset of core collapse, and then we go back roughly 650 to 700 seconds, and then we start our numerical simulations in 3D from there. No neutrinos, of course. And this is using a specialized version of the Flash code, which was developed by Sean Couch and Carl Fields and also other people. We use approx 21, which is a very simplified burning network. And we use an AMR grid, and the finest resolution is around 19 kilometers, 19, 20 kilometers. I will say here that using a small burning network is probably not great. There's a lot of intricacies, especially of the late stage burning. And silicon rates is, for instance, one thing that we should worry more about. But you kind of have to start somewhere. And using approx 21 in MESA is easier, and it's also then we avoid any mapping issues when we map into the flash code, right? Like we did do this, we did some tests with using a larger network, and when we do the mapping, we don't see that many differences. We can map relatively well from a large network to a small network, but there is some subtleties there that you kind of have to deal with numerically, which we kind of want to avoid. And yeah, so this thing here. Eventually, what I want to do is I want to try to do a follow-up study to this and have a much larger network and try to maybe use FlashX, which can support this, or maybe we will implement a larger burning network into our current flash code. But this is work for the future. So here are some results. These are, as I said, fresh off the computer. I came back from vacation on Monday, and these slides are from Monday. So these are the first 3 models that I did. These are entropy slices in the XZ plane of the simulation. And this is the 3 first models that finished. This is roughly 50 to 100 seconds before the onset of core collapse. And as we very clearly see here, if I can make my pointer work, there we go. There are this large-scale structure here. So what we're looking at here is the oxygen burning layer. And there's this large-scale structure. This one in particular has this kind of like quadrupole structure. And we all see this kind of turbulence here that has developed. And I mean, at this point, this is nothing new. People know this. There's people here in the audience who have done studies on this. But it becomes clear now that all this turbulence will seed asymmetries that will be important for the core collapse explosion and the development of the shock as it propagates through the star. I should also mention that we can also have burning here in the inner regions where the silicon layers sit. This is just a bit difficult to show on the same plot. And of course, that will also be important for the earlier phases of the explosion. Now, I think, so what we will do is that we will run this, and then we will run at least 1 or 2 comparisons in 3D, where we will start from the MESA model, and then we will start from this model, and then we will look at the differences. I think it will be interesting to see how these large-scale structures influences the late-time gravitational wave emission. But this is, as I said, a little teaser of the work that will be done in the future. And I think this is the natural next step to do in the kind of the whole picture of core collapse simulations. And there are some people who have done this. There's this one very nice study by Robert Bouling where they go from 7 minutes before the onset of core collapse to something like 7 seconds after. That's a very nice title. But it's just one simulation, right? Only one simulation. And many modern simulations, they still start from 1D progenitors. So I think that's something that we really need to get working on. So more updates on this in the future. Okay, so that brings me to part 2. If there's any quick questions from part 1, I can take them now, or we can take them at the end. Coulter, do you want to?
So when you get a lot of this turbulent motion before collapse even starts, have you guys calculated the gravitational wave signal from this?
That is on the to-do list. So the question was, can we do gravitational waves from this? My expectation is that they will be very weak. But that is actually on the to-do list. That's a very interesting question. Yeah, so okay. Question was, what is the central core? The central core is the iron core surrounded by a small silicon layer in these models. Yeah, not all of the models have silicon burning, but some of them do.
Yes, very cool work. So a few questions, short ones hopefully. Do you see that there's a larger, we evolved on these models, and we saw what Bernard saw in his conclusion that 3D perturbations are more conducive to explosion. These are the first set from Flash and the first set that Bernard developed. But do you see that if you crank up at the isotope count, do you see a smaller core YE?
This I'll have to get back to you on.
Okay.
Like these are literally fresh off the computer, and all of the analysis is to be done in the upcoming weeks or months.
And then secondly, do you add perturbations? Because Carl Fields saw in his paper that if you don't add perturbation, you get this boxedness. I'm concerned that the quadrupolar moment could be a Cartesian box connected.
So the quadrupole thing could be a Cartesian thing, but we add perturbations, but they're at much higher L numbers, so they're not responsible for these structures that we see.
Okay, thank you.
Okay, so then, unless there's, okay, one more quick. These are more than I had anticipated, so now I have to go faster. Yeah, it's careful what you ask for.
Yes, I have a comment and a question. The comment is that the 21 isotope network is certainly not suited for this kind of calculation. So you must necessarily increase the number of isotopes. My question is that one of the main issues for concerning the late stages of massive stars is the occurrence of the oxygen-carbon shell merger that may deeply affect the final structure of the star. Are you able to find this kind of phenomenon in this simulation?
At this point, we're not able to say something about that directly. I mean, we go back something like 600 seconds or so, and we rely on all of these 1D MESA models. And so all of these subtleties we'll have to kind of study even going further back and worrying about. But this is more of a first step in that direction.
Okay.
So no, to answer that question. Okay, part 2, late time gravitational wave emission. And I just want to very quickly describe where this comes from. I forgot to put the figure label here. This is from a paper by Ewald Müller in 2012. So the late time gravitational wave emission is generated by two things. It's either this asymmetrical neutrino emission that you see here. So this is a surface plot, kind of, you look at the whole sphere and you can see these hot spots and cold spots in the neutrino emission. That can generate gravitational waves because, as we all know, the neutrinos, they carry away most of the energy, right? So they contribute significantly to the stress energy tensor. Additionally, as the shock propagates out through the star, this can happen in an asymmetrical way, and this will then also generate this low frequency signal that we have seen a few examples of already. So in this project, we will perform up to 5 3D simulations. 4 of them are running. One of them is exploding. I'll get back to this plot later. The goal is to do 1.5 to 2 seconds. And you see one of them has already reached a significant fraction of that. The motivation for this is kind of the work that we started doing with Coulter, where we wanted to look at this part of the signal, and we found that there was actually very few complete signals in the literature. We used, in this initial study, this data from Anne Bongarat, which was very nice. They had the data going from bounce all the way until shock breakout, but the neutrinos were turned off at something like 1 or 1.3 seconds, depending a little bit on which model. And they were not fully self-consistent. So there's simply a need for more predictions of this kind of signal. And then additionally, recently, while this project was in the startup phase, there was this very interesting results coming out of the Princeton group, where they ran a large set of simulations. And some of these results have been published in other papers, but this Choi et al. Paper is the main paper for the gravitational waves. And they predict very strong strains for the low frequency signal, right? So if you go to the literature before this, you could see values of 10, 15, 100, maybe a little bit more. But these models, some of them, they reach values of a few thousand, or like 1,500 centimeters. So it's quite large. And of course, this is very important for the detectability. So at 10 kiloparsec, they estimated the signal to noise ratio of around 1,000 for some of these models. And in the LVK, and using a detector like the SIGO, 4.5 or something thousand for some of the more extreme models, which of course means that these are very, very detectable events. And then throwing out maybe a controversial statement, maybe LIGO is the wrong machine. The LVK is the wrong machines for looking for gravitational waves from core collapse supernova, if this really turns out to be true. So this is quite interesting, right? So briefly, the simulation setup. Yes, we start from 1D profiles. These 2 projects were started out of sync. So I do the thing that I just said we shouldn't do. We use Flash again. We use a specific neutrino transport that I developed to do this kind of long-term and faster simulations. It's a gray or an energy integrated M1 scheme. Again, we have AMR, and we have a finest resolution of around 350 meters. When I designed the study, I picked out one of these models from the Fornax simulation suite, and I really tried to say, okay, I'm going to pick out a kind of a middle-of-the-road model, one that is neither extreme in explosion energy nor weak in explosion energy. It doesn't have a very strong gravitational wave signal, doesn't have a very weak gravitational wave signal, to have a somewhat fair comparison. So I picked this S15.01 solar mass model, and then we have the other models were also then picked from this set of Suckbolt models that came out well, by now quite some time ago. I want to talk a little bit about this gray transport thing because there are some neutrino transport experts here in the audience. Of course, you would like to use the most complicated neutrino transport possible, right? Because that's really what drives the explosion. The problem with that is then it becomes difficult to go to really late times, and it becomes difficult to do really many simulations. So I spent quite some time developing a energy integrated scheme and kind of tuning it or matching it to our energy integrated scheme, which was very nice because we have this high fidelity energy integrated scheme, so we can kind of, in the same code, just see what happens when you change the different parameters of the gray scheme, and then you can achieve fairly good agreement. And this is an excerpt from this paper and from a few different progenitors using the SFHO equation of state. In blue, you see the results from the energy dependent, no, from the gray, and in red you see from the energy dependent, and this green curve we can just ignore. And we're looking at the shock radius and the proton-neutron star radius over here as a function of time after bounce, and these are all 2D simulations. And as you see here, you see relatively good agreement between the energy dependent and the energy integrated scheme in terms of things like explosion time and shock trajectories and stuff like that. Proton-neutron stars tend to be a little bit more puffed up when you do the energy integrated transport. And in general, I would say that energy integrated is a bit more explosive. It's a little bit more energetic, at least in 2D. Just expanding on this a little bit, if you were to look at the neutrino quantities, so something like the average energies and the luminosities, so we have the three species that we track, the electron types and the heavies. And the heavies are a bit difficult. There, the average energies disagree a little bit, and this has to do with this semi-transparent region in the outer proton-neutron star, where this energy-dependent scattering is quite important. And of course, we cannot track inelastic scattering in our energy integrated scheme. So that also has an influence on this. But for the other two species, the agreement, I would say, is fairly well. Okay, so that was just for the transport experts. If you care about the observables, the gravitational waves, you see, so this is one model that was ran with the two different transports, the same progenitor, same equation of state, and you see that the gravitational wave signals, they look fairly similar, right? They're a little bit different, but there's always difference between core collapse supernovae models. If you pay really close attention, you will see here that the frequency is a little bit lower here, and if you know your mode analysis, that's because the proton-neutron star is a bit more puffed up and you get lower frequencies. Okay, so getting back to the 3D simulations. First disappointment, the 15.01 solar mass model did not explode. Right? So the model that I picked out to compare with the Fornax model did not explode. This more massive in red here, this 30 solar mass model, that really looks like it's exploding now. And then we have another S12 model that looks like it's also not going to explode. And then we have a 21 solar mass model that also, I think, will end up exploding just because of how it is evolving. It's hard to see here. It's this kind of purple line here. It has not evolved for that long. And then we need to do the fifth model, which I will start soon. So coming back to this comparison model, you know, it did not explode here when the interface fell through. And it's been going now for almost 600 milliseconds, and it's showing no sign of explosion. So that, as I said, makes it quite hard to compare with the Princeton group results. If you look at the gravitational waves from the matter from this thing, it looks what you would expect. You have an amplitude of a couple of centimeters, stochastic and random looking. And if you were to do the Fourier transform of this, you would see this typical ramp up that you see in all modern signals. Looking at the gravitational wave emission from the neutrinos. So this is the strain associated with asymmetric neutrino emission. again, as a function of time after core bounce for an observer situated at the equator. And we get here, amplitudes of a few centimeters. And I mean, this is kind of consistent with the literature. What you see, if you have these non-exploding models, they can be in this range. They can be a bit smaller. But yeah, this again, it's if you have an exploding model, we would expect larger values here. Again, a bit unfortunate that we couldn't compare directly to the Princeton work. And I realized that I have talked much faster than planned. So we'll have time for some questions. I just want to say that kind of a summary instead of conclusion. I think it's really important to start moving towards this multidimensional progenitors. And while we need to increase we need to have the best physics there we can, anything is better than a 1D model. Well, maybe not anything, but they're at least a good step in the right direction. And I really think these gravitational waves are quite interesting. The late time emission is quite interesting, and maybe we should really, as a community, think if we should try to explore this part of the signal a bit more to help motivate detectors like this IGO to build the science case for other types of detectors. So, thanks.
Thank you. We have time for questions. Yeah. Okay.
I get it before you because you're gonna ream him. So this is a question for you and for the rest of the neutrino transport people in the audience. From Chioni's talk yesterday, a full Boltzmann solve, very expensive. When we're talking about these M1 schemes, a gray transport scheme is cheaper than a spectral transport scheme. Is there a way that we can move forward in our simulations as a community of starting early with a gray scheme up until collapse, and then maybe finding a way to transfer to a spectral scheme, and then maybe after a second or two, when the protoneutron star cools down, the neutrino emission is more regular, we can transition back to a gray scheme to get some of these very long-term signals that you're talking about?
So we have been thinking about doing the other way. So do the critical phase up until explosion using a more advanced scheme, and then maybe transitioning into a simpler scheme at the tail end of the simulations. I think is maybe easier to do. You have to worry about the details of the microphysics when you're doing your collapse and stuff like that, and when you're doing the explosion. So yeah, it's a bit tricky. I would maybe do the other way around, switch to a simpler scheme at later times.
Yeah.
And then Tony.
If you can go back to the spectrograms for the 15.01 in gray and with energy dependence.
Yes, this one.
Yeah, that's right. So in gray, you don't get prompt convection, is that right?
Yeah, okay, so this is a detail. The 2D ones, we ran them for the whole collapse in 2D, and we get prompt convection.
Okay.
The gray ones, since I don't want to mess up the microphysics of the collapse, I do it in 1D with the full transport, and then I switch some 10, 15 milliseconds after bounce.
Got it.
And then you don't get this.
And then a quick follow-up. Can you do another model we published in Choice paper or in my early 2023? Can you just do another comparison?
Yeah, so we can. I mean, the gray scheme is fast. It's like 5 to 7 times faster than the energy-dependent one. I still have time for maybe like one more model. So the question is, yeah, we have to decide which model to do.
The 17, because that explodes with a high energy.
Yeah, maybe that will be a good thing to look at. I need to think about it a bit.
Lastly, the SASE here is very visible. Like in the 15.01, you can see the SASE oscillation, the shock radii after half a second. Do you see what the neutrino signatures are for these? Like, what is the strains for the?
This need to be looked at.
Okay.
This will be, look for the results, look for the paper.
Yeah. So Haakon, beautiful work as always. And I love your approach, to sort of broaden out in this way. So you mentioned two very important things with which I want to concur and then comment. One, we definitely, and I'm going to press Marco Limongi on this when he speaks about, push the stellar evolution community. We really have to figure out a way forward there. The other is, you said, that you were asking if it would be valuable to, move in the direction of exploring this late time stuff, absolutely. I think the main thing we need to keep in mind, and for this broader community, so it's all good to, for example, use a great treatment and therefore be able to run longer and run many more models and explore the possibilities. And that's excellent, needed, and has great benefit. However, it's also important for us to understand that when we look at the outcomes from those models, gravitational wave signatures, neutrino signatures, et cetera, we have to keep in mind what went into the models to produce those. So, for example, in a given situation, whatever the progenitor is, you predict an outcome for gravitational wave emission, you predict an outcome for neutrino emission, but the treatment of the physics may actually not necessarily give you the right answer for that progenitor. All right, whether it should explode or should not explode, et cetera. So I think the main thing is, yes, absolutely, these landscape studies are imperative. Obviously, the focus on 3D progenitors, couldn't be overemphasized. But not all, we need to keep in mind for every signature that we provide to the observers, the observers need to keep in mind, those signatures need to come along with a qualification as to, how those signatures were produced, what were the specifics of the models, what was the physics included, how was the physics treated, because this is a problem 60 years has taught us is very sensitive to detail. 10% effects can change the outcomes qualitatively, as you had emphasized earlier on. So that's the comment I have. I mean, it's all good, but we really do need to understand whatever the outcomes are in context. That makes sense?
Yeah, it was more of a comment than a question, but I fully agree with this. One thing I should mention, by the way, the outcome of these progenitor simulations, we aim to do around 10 or 15 of them. They will all be publicly available if people want to have them as initial condition. That's kind of the main goal of this study.
So I was going to carry on with the progenitor discussion. So you do these progenitor simulations, you're doing the convection. There's limitations to do this even when you're doing it in full glory, your viscosity is high and stuff like this. Can you actually come up with a range of kind of the characteristics of the like density variations and features like this and entropy variations that then we, maybe as a community, we can then study the range of possible results from the progenitors? Can we get to, instead of saying, I'm going to run this and then collapse it, to I'm going to run it, understand what the physics is, and then that guides what's the range of answers we can be getting?
So, I mean, if I understand your question correctly, this kind of comes back to the idea I have of doing many of these, right? Like, we need to do many of them. And so let's say I have a MESA model, I run it with some network, I have some initial mass, and I'm like, nobody should claim that this is exactly what will happen for this star, right? But if you do a range of these, and if you do many of them, and we now at the point where you can start to do actually a lot of these stellar progenitors in 3D, well, a decent amount, right? Then you will have some idea of the range of outcomes that is possible, and still with all of the caveats of your resolution and your treatment of everything. So but yeah, this is kind of the goal of this whole thing.
Yeah, thank you. Do you know when the Flash models will be public?
Okay, so this project has a runtime until early next year.
Okay.
Then the paper has to be written, and then the Flash files will be public.
And last, do you think the 15.01 lack of explosion could be just neutrino microphysics, like the absence of inelastic scattering off nucleons?
I mean, it could be, but it could also not be. I mean, as I said, if I've seen any trend in the difference between the more sophisticated neutrino transport and treatment, is that the gray tends to be a bit more explosive. So, that's compared to kind of standard flash, what I would say. Yeah.
Thank you. I think we should move on. Thanks again, Haakon. And next speaker, yeah.